I'm recording this. Hope that's okay. Yeah, so we'll put this on at the end if we end up talking about anything. So I'm gonna go make myself a snack. Anybody who has something they want to talk about, that's literally the point of this. Tell me what it is so that we can talk about it. Okay, I'll be right back. So I hope when I get back there's something in the chat. See you. All right, what's up? Gotcha. Oh yeah, I can't even look there. I can look here. Right, so I'm looking at the web sign homework. All right, Darren says, could you go over arc length, surface area, and volume, just the concepts? Absolutely, absolutely, perfect question. Thank you. So I was also just looking at the man, y'all are already on this stuff. Oh my goodness, I thought I had a little more time here. So homework 6 to 8 is what's going to be on the next test, huh? Okay. Cool. All right. Yeah, I don't let them market to you hastiness as rigor, if you catch my meaning. Universities like to repackage their hasty classes as rigorous, and that shit pisses me off because that's not what it is. Okay, so oh, hold on, sorry, I do need to check one thing. Okay, so right, so arc length, surface area, and volume. Absolutely, I can talk about that. Absolutely, I can talk about that. So let's first talk about arc length for a second. So consider these two curves. Let's say this one, or I should say f of x. Let's say this is from 0 to 1, right? Versus, let's say this curve from 0 to 1. Now they both cross through this point here, 0, 0, and 0, 1. Right? In both of these functions, you plug in 0, you get 0. You plug in 1, you get 1. I said the wrong thing. I said 0, 1. Of course, I meant to say 1, 1. Right? You plug in 1, you get 1 in both of those functions. So they both go between the point 0, 0 and 1, 1. But one of them goes in a straight line and the other one goes in a nice little curve. So can you measure the total distance along those two paths? So the distance from there to there, or the distance along this path as well. First of all, which of those two distances is longer? Right? It should be intuitive that the second one is longer because you're going between the same 2 points, but instead of going in a simple straight line, you're taking more of a diversion, right? You're going on more of a curvy path. So necessarily it's going to be longer than just a straight line. How can you calculate both of those? Well, when I was first learning calculus, it was tempting to me to say, well, it's clearly just the integral from 0 to 1 of a tiny little step, which is just, dx, right? So, take a tiny little step along this direction. And so it's just, add all those up and then boom, there you go. So it's just going to be that. Whoops, I forgot that's behind me. So it's just going to be that, right? But the problem is this one you're kind of led to the same conclusion. And so it's not as simple as just the sum of dx, because then it doesn't depend on what you have going on, right? Instead, it's the sum of this other thing that we made up called ds. Now, what is ds? Well, the idea is, instead of taking a little step in the x direction, or instead of taking a little step in the y direction, what you're really doing is going in this diagonal direction, right? So this little, it's not a little step in the x direction or a little step in the y direction. It is like diagonal. And that diagonal is like changing the whole time as you go along, right? Like for this curve, it starts off with like a shallow diagonal, but then the more it goes up, the more it becomes like steeper. So that ds situation is changing relative to the dx and the dy as you go along, right? And the relationship between them at all times is they make a right triangle. So they always have this relationship with each other. And if you solve that for ds, right, you can get ds is the square root of dx squared plus dy squared. And if you want to, you can even rewrite it as that. So the point is, it's this other differential object which is related to the ones you're familiar with by this equation. So if you want to add up all of the little tiny links, and those little tiny links aren't all horizontal or aren't all vertical, they're kind of changing. The little tiny links are changing direction. You got to use this ds thing instead of just the dx. Which means you pretty much are using a dx, you just got to add in this extra thing. So let's do that. It's the integral of ds. And then ds is the square root of 1 plus dy dx squared. Or in some contexts, it's easier to say f prime squared. And in this case, this function was just x. So this turns out to be 1 plus, well, the derivative of x is just 1. So this turns out to be the square root of 2. So this turns out to be the integral from there to there, which turns out to be this, which turns out to be that. Oops, I forgot that was below me. Right. So yeah, so it turns out that the total length of this thing from there to there, the total length of this blue line segment is the square root of 2, which perhaps you already knew from geometry, but it's cool to see that you can produce it with calculus as well. Now let's compare that to the parabola, which would be exactly the same thing. It is the integral from 0 to 1 of ds. It's just that ds is different for this one. For this one, it's well, I guess I should work it out on the side like I did here. For this one, it's the square root of 1 plus f prime squared. It's just that this time f is x squared, which means f prime is 2x. Right, so it works out like that instead. And I should be clear, the dx is outside of the square root. It is not inside the square root. So yeah, so it turns out that ds is equal to the square root of 1 plus 4x squared dx. And so that's what we would be integrating from 0 to 1. Yeah, now how do you actually do that integral? That's the whole thing, because this is just going to work out to be like weird. It's going to be a pain to do this integral, so we're not actually going to do it. We'll ask the computer instead. Can I easily wait a second. Actually, yeah, hang on. I can just do it on here. Oh, hold on. I gotta change this too. Okay. Okay, check it out. So it's the integral. This is Desmos, by the way, desmos.com or Desmos the app. You can literally just type the integral from 0 to 1 of whatever function I want in the whole world, dx, and it just calculates it for me. How gorgeous is that? So that is the area, sorry, that is the length of the curve y equals x squared. Y equals x squared from 0 to 1, right? The length of that versus the length of that, right? So between here and here, right, the lengths of those two curves, it turns out that the green one is the square root of 2, 1.414. But the blue one is that number there, 1.478. So yeah, the other one was, it worked out to be the square root of 2, right? So that's the green distance versus the blue distance. So anyway, so that's the arc length, right? That's how you calculate the distance along a curve between 2 points, right? And it involves this funny object ds, which is the whoops, I better switch back. It involves this funny object ds, which is kind of at the heart of it. So yeah, so let's talk about then surface area and volume, right? So if you have a curve, like say this one, it is a common notion in your class these days to imagine rotating that around one of the axes. So let's say rotating this around the x-axis. So it's like with each of those values, you like rotate the entire thing over and make like a rotationally symmetric thing. So each one of these points on the curve becomes a whole circle or a whole disk, depending on how you are interpreting it. And so it just makes this sort of large three-dimensional object. And that three-dimensional object, you can calculate things about it. Like, for example, you might want to know what is all the space inside of it, right? All the space on the inside, you know, the total volume of that three-dimensional object. How can you figure out what that is? Or maybe you just want to know about the space on the outside, like the area along the outside of this object, right? So not on the inside, like how much, you know, air fits on the inside, but instead like the surface area on the outside, like how much paint can fit along the outer surface of this thing, right? Those are two different things, two different kinds of things you're measuring, right? Three-dimensional space versus two-dimensional space. But both of those can be done with an integral, right? So let's first talk about the volume. The idea behind the volume, right? The volume of that horn-shaped thing is like what you get if you add up all the disks on the inside of the horn-shaped thing. So we've got, you know, this big outer circle at the very end there. And I know you know how to find the area of a circle, right? It's just pi r squared. So you just take this radius, whatever that is, do pi r squared to that, and that's the area of that one circle, right? So just one circle, infinitely thin, just the very last circle there. But if you think about it, this object is made of tons of those circles. For example, this one, right at that point on the function, this gets revolved to make this circle. And that circle also has a certain area that you could calculate using pi r squared. It's just that that radius is going to be different. It's going to be smaller for that function, you know, down there. And so, you know, I'll call this, you know, f, whatever f happens to be. So yeah, and it takes on different values, right? It's big down there and it's small down there. And then somewhere in the middle, it's in the middle. So this circle has its own radius. And so if you do pi r squared to that radius, it's going to have its own area. So all of these circles have their own areas. Here's the key idea. If you take all of those areas, all infinitely many of them, and you add up all of those areas, all infinitely many of them, well, together, that's going to be the full volume of the interior. So intuitively, it's like this. It's like if you have the area of just one of those circles, but then you sum them all together, well, then that's going to be the volume of the whole thing, right? So fundamentally, that's what's going on, is that you're adding up all of these circles and combining them together, stacking them together to make the full shape. So to be a little bit more formal, what I'm saying is you take the area of just one of those circles. So for, you know, for each of these circles, the radius is just whatever the current value of the function is, right? So we're at like a certain x value at each of these points, and then the radius is just f of that x value, whatever it is, right? So the current radius is just f of x, and so that means the current area is pi times f of x squared, right? So that little expression there, pi times f of x squared, is giving us the area of these circles as we move along, right? So as x ranges from whatever this is, let's say this is 0 to let's say 10. See, I'm not understanding do not disturb because, all right, this is, like I said, this is a new setup, so I'm trying a new situation. I don't have it quite working properly yet. Can't have that. That's no good. Anyway, so that's the expression for one of our circle areas. So all we have to do now is add them all together. So take from the teeniest, tiniest circle at the very beginning all the way to the huge circle at the end, we want to add all of those together. And that's exactly what it means to do an integral from 0 to 10 with respect to x, right? Going from left to right, we're adding up all of those different disks, right? And the disks, and here's the important thing to understand, the disks are being stacked in the x direction, right? They're being stacked on top of each other from left to right. So that's why we're going from left to right in the dx, right? So yeah, so if you calculate this integral, then that's going to be the total volume of that thing, right? Because you're literally stacking all of these disks together. So please try to see this formula as literally the sum of a bunch of circles, right? It's literally pi r squared, add them all together, right? That's literally what it is. That's not a trick. That's literally why the formula is that, because you're literally adding together all the circles, stacking them up to make the volume of this thing. So yeah, so that's why the volume formula is that. But now let's talk about the surface area. So the surface area of a shape of that sort is kind of the same situation, except this time we're not interested in what's happening on the inside. So we're not interested in the areas of all of these circles. We're only interested in what's happening on the outside. So I'll use a different color here. We're only concerned with the circumferences of these circles. So this time, instead of taking the areas of all of those circles and adding together all the areas, which would be like getting the full interior of this horn-shaped thing, we're only doing the outside. We're only interested in the distance along the outside and stacking all of those together. Stacking all of those together, right? So yeah. So the way it's working is instead of taking the areas and adding all those together, we're going to do something very similar to that, but this time we're taking all these circumferences and we're stacking all those together. So just as the formula for area is pi r squared, and so we did pi times whatever the current radius squared is, now we're talking about circumference. And the circumference of a circle, recall, is 2 pi r. And so for us, that's 2 pi times r, which is always changing. So it's just f of whatever your current x value is. And then we want to add all of those together. But here's the thing. It's not dx, because dx is like, here it's like all of these circles are being stacked directly on top of each other. All of the centers of these disks were all like stacked in a straight line. But now that we're looking at a one-dimensional thing, it's kind of different. You have to account for the fact that these circles themselves are not really stacked on top of each other. They kind of fall through each other. They're stacked in like a curved type of way. So I know I'm being a bit hand wavy here, but the point is, it's ds, not dx, right? Is the point. Which means you got to replace. Well, one thing you can do is you can pull out the 2 pi, right? So sometimes people like to write the formula this way. You got to replace that ds with this square root thing from before, right? But yeah, once you do that, that's the formula, right? And then again from 0 to 10 or wherever. So this formula is going to give you the total amount of area on the outside of the circle, or of the shape. And this one's going to give you the total volume on the inside of the shape, right? So let's compare these three types of integrals we've discussed, right? we first discussed this one, which is giving you, notice, the one-dimensional length of these curves, right? Is giving you something in meters or inches or feet, right? Is giving you a simple length, a simple distance from, as you travel along in a regular, normal, one-dimensional thing, right? Now you might be turning and so on, and that's the hard part, but the final answer is in meters, and it's just a length, just a distance for the arc length. But then we discussed this one, right, which is where if you have a three-dimensional object and you want to find the total amount of volume on the inside, right, this type of integral asking for a volume, of course, the final answer is going to be in cubic meters or cubic inches or cubic feet or whatever, right, because you're talking about a three-dimensional thing. And then finally, this one we were talking about the area along the outside of the surface, so just the outer shell of it, right? So that's only a two-dimensional area. So that should be meters squared or square inches or square meters or square feet or whatever, right? So yeah, so all three of these integrals, the best way to not get confused between them, in my opinion, is to think about that. Think about whether you're talking about a one-dimensional thing or a two-dimensional thing or a three-dimensional thing. All these integrals are different, right? Length versus area versus volume, right? 1, 2, 3 dimensions, all different. So yeah, so that was general overview of area and volume integrals. There are a couple, for all these, there's like, sometimes multiple ways to go about them. But yeah, this is how I think about them. I strongly recommend, to help you remember the formula, I strongly recommend that you think of this as, at least this one, of these volume for the disk, is that the volume is the sum of all the areas, right? You can think of it like that, right? It's like pi r squared dx, whereas the surface area is the sum of all the circumferences, right? So you can think of it as the sum of all the areas versus the sum of all the circumferences. And the areas together stack up to make the full volume of the interior, right? All the filled in disks stack on top of each other to make the filled in horn or whatever shape. Whereas here, it's just the circumferences. It's not the full disks with the interior. It's just the outer edge. It's just the circumferences, the circles themselves. Those stack together to make not the filled in horn, but just the outer shell of the horn. In other words, the surface area of the horn, right? So yeah, areas stack together to make volume. Circumferences stack together to make surface area. That is the intuition to have, and with this intuition, you will be far more powerful at remembering the integral formulas because there's a rhyme or reason to them. Yeah. Okay. Who asked that? Darren. Yeah, I hope that was helpful, Darren. General overview. If you'd like to go over a particular example, finding the area or volume of a certain solid or whatever, we can totally do that. Okay, I got a snack, but I didn't make it yet. So I'm gonna put peanut butter on this English muffin. Somebody hit me up with another topic if you'd like. These English muffins are named after an attendee. Oh, you can't see it because the green screen thinks it's not a person. Not the green screen, I should say, the software that's trying to replicate a green screen, because the actual green screen is not working. Had some technical struggles today. Great question, Antonio. Will we be able to see our test somehow? Yeah, I'm sorry about the consequences here that you haven't gotten your tests back. Yeah, well, I guess I can give them to you when I come back to school. When would that be? That would be, well, I don't know. It'll be probably next week sometime. I have to get, my roommate and I have to get negative tests back. I don't know. How bad do you want your test? If you want it really bad, I can scan it to you and send it to you. So I guess I'll send an announcement about that. It's kind of a lot of them, so I'm kind of not looking forward to doing that. So if you want yours specifically, I'll send it to you. I figure most people probably won't, so I'd rather just do the specific students than the whole lot. Yeah. So anyway, answer to that question is I will send you your test if you specifically request it. So please send me an email asking for your test, and I will send it back to you. I don't mean to imply that that's a problem. I'm happy to do that. I just mean to say that I'm not going to do it for 50 students if only 5 of them want it. You know what I mean? So like so those 5 students can please email me, and I will happily send you your test. If it turns out to be 30 students, that's also fine too. Yeah. Okay. I'm actually at the moment in the middle of recording a solutions guide to the exam, so that should come out shortly. Just sort of me going through all the problems on the exam and discussing them and the related techniques. Yeah, I'm 2 problems into that. I meant to be doing it earlier, but like I said, it took me a while to come up with this recording situation. Yeah, so even if you don't get all your exams back, you can look at the solutions guide and think can't talk today. Look through the solution to any of the problems that you found to be confusing. That's what I'm trying to say. Okay, speaking of problems that are confusing, are there any more that you'd like to discuss today? We have 10 minutes left in the session now. Can we go through any problems? I did pull up the website. Oh yeah, that's probably the wrong one to look at though. Oh man, and improper integrals. Man, you guys really go fast. When I took Calculus II, I had it in high school and had an entire year to do it, which I think really makes it a lot easier. I think it really deserves an entire year, frankly. I don't think it's helpful or good to try and compress it so far, but whatever. I don't know anything. Okay, so yeah, so you had all these oh no, this was series, and then you also did these improper integral things. Oh yeah, here's some nice arc length stuff. Area of the surface. Gabriel's horn, gotta love that one. Gotta love Gabriel's horn. Such a funny thing. Not that different from what I drew here, honestly, although it's the other way around and it's infinite. I don't know if you got to that problem on the website, right? The funny infinite shape, it's an infinite solid revolution. And it has the funny property that its surface area is infinite, and yet its volume is finite. So it's like, here, let me. it's this, right? It's the thing, it's Gabriel's horn, like, the angel Gabriel. You imagine he blows his horn in, but it's infinitely long, and so it's got this funny feature to it that you can calculate both the volume and the surface area, and you can calculate that the surface area is infinite, and yet the volume on the inside is finite, which leads one to the strange conclusion that it would take an infinite amount of paint to paint it, but it would only take a finite amount of paint to fill it with paint. So that's kind of a funny thing. But that's probably why such objects don't actually exist and only exist in the mathematical abstract. Okay, so that's all I got. I can't really talk anymore and be entertaining for much longer than this. Is there anything else that I can help you with? Anybody got a problem that they want to talk about or anything like that? I mean, you all bothered to come, which is great. I'm glad you find it helpful, but I'm shocked you find it helpful since I'm not really talking about anything. So does anybody got anything they want to talk about? I want to be useful. I guess I better eat this English muffin. I never ended up finding a homework problem for double integrals. Well, that makes sense, Kylie, because double integrals, hello? There we go. Double integrals, as far as I'm aware, are a Calc 3 thing. You don't really do double integrals until Calc 3, as far as I have ever seen. However, as you can see, it's not really like a standardized thing. Everybody kind of does things differently. So yeah, so I don't think you're supposed to know about double integrals yet. Yeah, so maybe it's kind of weird how the professor's spending a lot of time teaching you things that are not part of this class, when at the same time it's kind of hard to understand the things that are part of this class because it's all compressed into one semester, when really it's literally 100 years worth of material that humans discovered very slowly and painstakingly over time. Yeah, in fact, maybe this entire setup is fundamentally not conducive to what we're trying to do. maybe this whole way of learning is actually garbage and should be rethought from the ground up, and we shouldn't have fucking whatever. Anyway, right. So best I can do to help is just ask if there's any questions left, but I think I've asked that enough times. It sounds like there's nothing else anybody wants to talk about, so we will call it there for today. Hope that was helpful. Definitely we'll be posting the exam solutions hopefully later today or possibly tomorrow. Yeah, that'll be on YouTube. Okay. Have a great day, everybody. Bye-bye. Oh, that's right, Eric. Wait. Oh, okay.